Everybody, our next speaker is Derek Bingham, also one of the organizers of this workshop here, and he will talk about Bayesian model calibration for generalized linear models and application in radiation transport. Looking forward to your talk.
All right, well, thanks a lot. So what I had intended to do was actually give an introduction to model calibration, and through the series of talks we've had, anything I would have said has been said. So my talk has evolved, and this is going to be a bit of an applied statistics talk, but actually what I'd like you to take from it, if you're not a statistician, is where a computational model fits in sometimes in a big science project. And actually this project is about developing the model in some sense. So you'll see how that comes along. So I'm from Simon Fraser University, which is in Burnaby, just outside of Vancouver, and I'll talk about that in a second. But the person who did all the heavy lifting was Mike Grosskopf, who was a PhD student with me and subsequently moved to Los Alamos National Lab. So for those of you who met Jim Gadiger over the last month, Jim is Mike's boss. So there you go. And our funders was the Department of Energy, but this is a collaboration between researchers at Simon Fraser, my group, and also at Texas A&M. So some of you might know Jean Ragusa and Marv Adams or Jim Morrell, who work with radiation transport. Is it all okay? Oh, okay. And some people, I've heard Tom Manteufel's name mentioned a couple of times while I've been here. Tom's part of this group as well. So I'm going to talk about an application, some methodology, and I'm just going to run through. I'm going to skip the outline slide, but it's the traditional one we have. I'm going to talk a bit about the application and what we developed. But I think the takeaway here is a bit of the procedure, the overall framework that we're working within. So somebody asked about Simon Fraser. Actually, Michael Goldstein said, well, I need to have some good pictures to set this up. So this is my university. So I'm a faculty member outside Vancouver. Some of you who are Battlestar Galactica fans, this is for you, Michael. The university was the set for New Caprica, apparently. Oops. And the most important spot on the campus is my office, and that's where the green arrow is. And so if you ever need a coffee and you're wandering around, you'll find one there. Trust me. Okay. All right. So, and that's the sunset from the office. So there you go. Anyway. All right. So if anybody wants to come and visit, it's not a bad spot. You can't stay with me though. But anyway. All right. So the area that I work in formerly was called computer experiments. It's kind of morphed into UQ, but it really has to do with what we would call performing an experiment, or basically looking at what happens to a computational model as you change the input. So it's exploring that response surface. Right. So all of you know this, that many of these models are they have a lot of different features to them. Sometimes require a large amount of computer time. Sometimes these are finite element sort of things, PDEs. Sometimes they have high dimensional inputs. Sometimes they have low. Basically, there's a lot of different computational models. I don't have to sell people here on that. The models that I'm going to talk about are not going to be available on your desktop, and in fact, these are running at the supercomputers at Los Alamos or at Lawrence Livermore National Lab. And so a lot of the things that I've dealt with, we don't have the ability to do sequential design or history matching or anything like that, because we would go off and we would submit, we'd say, please run these trials, and then we have to wait. So for some reason there's a timer on this right now, I'm not sure why. Apparently I have to speed up. Anyway, so one thing that we dealt with is a paper in the Astrophysical Journal about a design of an experiment that was accepted in 2016. The runs were submitted, and they should finish this year. That's 100 evaluations of an N-body model. So there you go. So some applications my group has worked on with Matt Pertola. One had to do with an upper atmosphere, a magnetosphere sort of calibration model. We've worked on ones with radiation transport at the bottom. There's a cosmology problem, and also nuclear physics and glaciology. So we've worked on a fair bit as a group. But the commonality is there's a model. There's a computational model, and we usually want to combine it with data, right? So that's part of the issue. So some assumptions for this talk is that the math or physics model is computationally intensive. It doesn't have to be. The response is a scalar. That's more for presentation as much as anything else. The model response is going to be a smooth and continuous function of the inputs in some d-dimensional unit cube. Again, these things we can change these, but for illustration, it's probably best to do that. The computer model is meant to be an estimate or tell us something about the mean of a physical system, but again, these aren't necessary conditions, but they're useful for illustration. All right, so the application that I'm going to talk about today has to do with radiation transport, and this is this collaboration I'm part of at the Center for Exascale Radiation Transport, and this has to do with scaling things up. I mean, radiation transport's interesting, and it matters to this group of people in nuclear engineering at Texas A&M, but also what also matters is the kind of calculations that you can make and what it says about the real world. And so this collaboration is between, contains, within the collaboration, there are applied mathematicians and statisticians and computer scientists, nuclear engineers. There's a lot of people doing their own thing. So the code that we have is what they call PDT. It uses parallel deterministic transport. I'm not an expert on sweep algorithms, and I'm not an expert on meshing and things like that, but these are all important, and they're part of the thing that we're going to be validating is their implementation on using tens of thousands and up to 800,000 cores for calculations. We're working towards scalability for the largest supercomputers. So that's the goal of the overarching goal for the computers, how things scale up and what we have to do for implementation. And that's true on the UQ side as well. Okay, so let's look at an application that we're working on. So this is a very simple, conceptually simple application insofar as if you look at it, there's a graphite block. On the left-hand side is a americium beryllium source. So we've got that on the left-hand side. On the right-hand side, there's a detector. So you've got a source sending neutrons out into the world, passing through things like graphite and being detected on at the detector. Okay, so there's a lot of, conceptually it's simple. What's happening, but the neutrons are bouncing around the room, they're passing through air, they're being reflected backwards, and being able to model all the different processes what's going on and actually have obtained the Poisson counting statistics that we would expect is not always easy to do. Sitting as an issue is that our graphite blocks or bricks are not necessarily pure graphite, so there are impurities that each individual brick has, that may be water or boron or whatever is sitting within that graphite. So you don't have pure graphite, right? But all the calculations that we're doing is assuming that, and what we're doing is, well, I shouldn't say it's not assuming that, but we have an impurity concentration. But each brick may have a different level of impurity. So we're going to end up having to come up with being able to estimate a distribution of impurities at the end of the day. So calibration, model calibration, and UQ for PDT, for parallel deterministic transport, or for this model and this application is important for understanding or assessing the predictive ability of the computational model. So that's part of this. So there's a code development exercise going on, there's experiments going on, and there's also an assessment of what the code can do at any given moment. That's also happening. So this is all part of a big development. And if you think about what they might be doing at Boeing or somewhere else, it's not that somebody delivers a code, it's that the code is always being developed or frequently being developed, and you're getting new information and improving that code, or at least assessing the ability of the code to represent the physical system that you want at any given moment. So this is kind of mimicking what you might expect to happen at a big company or at a national lab. Since the funder's the national lab, we'll assume it's them. So our approach perceives, this also fits within what we're going to call a hierarchical validation sort of exercise. So I don't want to spend too much time on what validation of a computational model is, because sometimes it's a philosophical sort of argument. But what we're going to do is we're going to start with just the graphite brick, a detector, source. And then we're going to slowly increase the difficulty of the experiments as the project goes on. So take the graphite brick, cut it in half, move it apart, and now you've got neutrons flowing through graphite, out of the graphite, into air, back into graphite, and then to the detector. So now we made that a slightly harder system to model. And we were going to do this sequentially, so there's a variety of different sorts of experiments or levels of difficulty that we're going to, we do with our experiments, each time evaluating the computational model. So on our trajectory, on our road to including a duct, so that duct is that move it apart. When you move the graphite apart, you can call that a duct. So we have a bent duct and a slit, so there's going to be some slits in the graphite. So we're going to continually make that harder. Now, why would you do that? Well, the idea with these experiments is that processes get turned on, if you will, for lack of a better way to say it, as you get as the experiments become more complex. And the idea is that rather than just looking at the most complex experiment, if we start at the beginning and build our way up, then maybe we can identify deficiencies in the code because of the new processes that we've turned on from one experiment to another. Okay, so that's the idea. All right, so we have a good model in theory. So that's great. Now, we can't always compute what we would like to, so we can't follow all the neutrons through the entire room, but we can do quite a lot because we have lots of cores available to us, so we have lots of computing that we can do. One of the problems is that we just can't exercise the model as often as we like, but we also can't always exercise it at the fidelity that we would like. So there are issues with meshing and so on, but also the number of polar angles that you would have the neutrons flowing out of the source at, those sorts of things. Those are all discretized and limited, and there's some averaging that goes on and so on. So we have observations from our model, and at the end of the day we also have experiments, so that's kind of nice. And what we'd like to do at the earliest stages is to characterize the impurities in the bricks so that when we make predictions on experiments for other bricks, if you will, we have an idea of the distribution of the brick impurities. That's one of the things that we would like to do. And also, I'm going to say validate the model, if you will. So what we want to do, this is the calibration exercise, is to use our field data and our simulator to estimate parameters that might govern the model, so the impurity distribution, if you will. And we'd like to validate the model, or I'm going to say would demonstrate the model is correct. What I really mean is not obviously incorrect. Okay, that's probably the best I can do. Now, at the end of the day, at the labs, you can imagine what they often want to do is validate the model. They work on the model over here, and almost everything they're going to do with it at the end of the day is going to be an extrapolation. That's not part of this experiment or part of this project, but I guarantee you that's what they're after. Oops. Okay, this looks better on my computer. So we have kind of a setup. So this is going to give you a flavor of what's going on. We do a calibration experiment. So this is what I'm going to call the IM1 or the impurity model experiments. We're going to do some simulations of that physical setup. We're going to do the model calibration, and then we're going to go down and do a second simulation. So I'm going to make the experiment with the same level of complexity. So instead of having one graphite block, I'm going to put two there. And I'm going to make a prediction of what I should see, and I'm going to, that's my validation experiment, and I'm going to make a prediction of that validation experiment. I'm going to assess what's going on, or assess the predictive ability of the model. Okay, so that's where I'm going to lead you. Now we can continue to do this, keep going down there with each of the experiments that we have. Okay, so for the moment, we're going to look at three possible calibration inputs. So, in what you've seen before, there are some design or control variables. We're going to assume there are none, and right now we're going to model in terms of these three inputs. Now the inputs themselves are so there's some uncertainty about the source. There's the source radius, the axial source position. So kind of think of the dense part of the source, exactly where it is on in this little box from where it's located, and also the impurity concentration. The first two are kind of a nuisance parameters for us, but we want to characterize that impurity distribution. We have 64 evaluations of our computational model. So as I said before, we don't have the ability to just exercise the model over and over and over. And we have 64 evaluations. I think each one of these used about 80,000 cores for each computation. Tens of thousands of core hours were used. Actually, hundreds of thousands, I'm sure. We have six, in this talk, we've done more experiments since I put this together, but we have 6 graphite bricks in which we're going to do calibration with, and the responses are going to be neutron counts. Okay. All right, so switching over, oh yeah.
The impurity concentration is a single number?
A single number per brick, but it's really, I mean, it's going to be an average for a brick, right? Because it really is an impurity field, if you will. And we're going to put that as a number per brick, but we're not after, so you think about it, if we had infinitely many observations and we had a perfect model, I'm going to converge on a distribution because, so it's like an individual to individual sort of distribution. Because if I'm going to make a prediction on a future brick, I don't know what its impurity is, but I know that there's a family, there's a distribution that represents the average impurity across individuals. Yeah. Okay, so my inverse problem is actually to get a distribution in that sense. Yeah.
Can I just check? So does the model have 3 inputs, or are you just considering 3 inputs because of your design side?
So the question was, are there 3 inputs? I'm going to say there are 3 inputs once we've conditioned on the experiment, right? So the experiment is 1 graphite block, but as soon as I put 2 there, we have to, it's a different models, but it's hard to think of a continuum in geometry as I start drilling holes and creating slits and things like that. So you have to, so the X's, if you will, the control things are kind of hidden from you, and all the experiments are done on the same contraption, if you will. All right, so, okay, so rehash of model calibration. The main goals for calibration are going to be estimate parameters that govern the model, or in this case, a distribution. So I'm going to say it's inverse problem-ish, and build a predictive model for the physical systems with estimates of uncertainty. So I want to be able to make predictions on either future bricks or the same, or under the same system. So those are the two big goals, not the only goals of calibration, but those are the two big ones. And you can think of this as an attempt to use an imperfect, calibration in general, to use an imperfect physics model and noisy versions of reality to try to solve some goal, right? Because the physicists know a lot, they may not know everything, okay? And reality is noisy, and that's an issue, so how do you put these two things together? And that's really the calibration exercise, or the goals, I think, the broad goals of calibration. So there you go. So this is the Kenny-Nohagan model. This is a way to write it, where you think of the field model as having some mean. If you have a continuous system, if you're observing the mean directly, a noisy version of it. So you'd have mu of x, which is the mean, and epsilon being, let's say, white noise. Doesn't have to be, but suppose it is. And the mean itself is kind of written as a sum of the computer model at the right, or the best values of the calibration parameters, plus some discrepancy that you have. So that's kind of the missing physics argument. So that's what your delta of x is. Okay, so you want to use your field data, your computer model eta, and wrap all that together and say something about the field. Okay, that's the basic idea. So the spirit of what we are doing is is this, right? We have a statistical model. The observations and simulations are combined to give something that's better than just using one bit of the model. Okay, so we want to estimate the distribution of system parameters. In our case, that's one of the goals, is to get that distribution, or get at some estimate of that distribution. Okay, what do I want to say here? Actually, so that in order to speed up, so you can think of, if you put it in this framework, I'm going to change it slightly, but just the spirit of what you've already seen, we've got our physical observations written as the simulator plus some discrepancy plus the noise. But in this particular case, one of the things that we can do is we can also use some of the, because we don't expect there to be, we don't expect there to be actually a physical discrepancy, right? We expect that if we can compute everything, the error that we're observing, if we could resolve everything, the error that we are observing is actually numeric error, right? So that numeric error is the error bounds that people often will talk about when they're talking about a numerical analysis procedure. So in principle, that's the world that we would like to push the code into. Okay, I'm not saying the code lives there, but that's where we want to end up as a goal for the project. All right, so whatever error, sampling error that you're getting, hopefully, hopefully this part doesn't exist. That you just don't have any missing physics. That's the hope. All right, let me just say, I'm going to go through this really, really quickly in the sense that our computational model is slow, if you will. It's computationally expensive, and so we're going to use a Gaussian process emulator. We talked about this a lot, and I'm going to skip through the details because you've seen lots of it. Let me just tell you the reason we use it. The reason we use it is this. We've got this model, so that black guy is the computational model, takes you heroic amounts of computational effort to get those dots, those 5 dots, and you want to say something about this. Now, statistics is usually about signal and noise, and there's no noise on this. And so how do you represent this? You say represent it through a random function, which Aretha explained really well today. And so you do that, and now you want some basis of uncertainty, and those uncertainty come from the possible sample paths that a Gaussian process that passes through those data points with a certain length scale can possibly have done. So if it passes through the first point, it could have gone up and down, could have gone down and up, and you think of what you're actually getting as a random curve, right? So you're not getting Gaussian data, you're getting a random curve, and all the possible random curves could have done this. Now, so one of the things that's come up a couple of times, because I know there was a surrogate model. It's on here. All right, there's a surrogate modeling, it was a surrogate modeling group or workshop. One of the things that came up was that, it's got to interpolate, or you can't really use polynomials for this, but my contention is you can and get some of the same types of uncertainty. And this is from a paper of ours where we've we did Bayesian model averaging over a polynomial chaos expansion, and you get the same sort of qualitative behavior as you would get from the standard Gaussian process. So yes, you can do other things as well. Okay, so all right, so let's go back here. So we've got our model. This is the basic Kenny-O'Hagan slide that I had up before. And let me just tell you how this works in practice. So we said, we're going to use this Gaussian process sort of emulator. So what you start with is a computer experiment or a set of simulation trials at the inputs x and t. So those green lollipops that you see there, the top of it is the observation. That's what you observed at those particular locations. Okay, and before you've actually done any data analysis, you've got that top middle plot, and those are just the different values of t, right? So that's the calibration. That's the thing we want to calibrate. And beforehand, we haven't collected any data. I don't know what it is. Let's say it ranges between 0 and 1. And each one of those curves represents the whole curve at the value of t that I ran the computer experiment on, and the actual evaluations are where the green dots are. The next one over here is the emulator. It's a Gaussian process emulator of the dots on the far right, the top left. And once we've tried to match that with the observations, which were the black dots that you saw in the middle curve, what you get is a calibrated version of the simulator, right? So that's this stuff here. We've narrowed down the uncertainty in what t could have been. We've ruled some out, almost like the history matching guys. We've ruled out some values as not obviously good, and or obviously not good, and this. So we've narrowed down the uncertainty there, and then once we adjust for discrepancy, our predictive distribution over x, at least, the thing you can measure or adjust in the field, is what you see on the bottom right. So operationally, that's what's happening. You're emulating the response surface that you observed on the top left, and over on the top right, that's what you see. We adjust to the data that we see in the top middle plot. After that adjustment, we narrow down the possible values for that calibration parameter. We adjust for discrepancy and come up with a predictive distribution. So we learn about theta, if you will, and we learn about the model itself. So that's operationally what's happening. Okay, so again, so I'm going to write this in a slightly different way. So what I'm going to do is I'm going to say y comes from a distribution, and the distribution, we've been mostly seeing Gaussian, and that mean is going to be eta plus delta. And the omega that's on the far right just represents your statistical model parameters, and that would include the variance for the white noise and the parameters for the Gaussian process if we were fitting it. And why am I doing that? Because I want to switch over, because the data I have aren't continuous data. Data I have are counts. Okay, so we're going to do it slightly differently. So this is for people who do generalized linear models and statistics. You've seen all this before, but what I'm going to do is I'm going to say my observations come from some distribution. So in this case, let's say if you're doing counts, a Poisson distribution is a very natural distribution. And its mean, the mean of the distribution, or the rate for a Poisson distribution, is characterized by, we'll call it mu of x, and we're going to write mu of x as what? Well, we have to link that mean with the support, with the proper support. So it's got to be positive, for instance. We don't want a negative rate in a Gaussian, for a Poisson distribution. And so often we use a link function to link the mean and the observations, okay? And that link function for a Poisson is often a log link as an example, so you just take the log of everything, and that's where your mean function lives. So what we're emulating in the Gaussian process in this case is actually the rate of the Poisson distribution that's shooting us those neutrons for our case, okay? And then we can still do so where's that Kenny-O'Hagan model operating? It's a very simple switch. It's just operating on the latent mean, the unobserved mean system, and not the original process. Okay. All right. So there you go. So that's pretty much it. Now Gaussian process is pretty flexible, and it's going to kind of do, even if you didn't do this change of support, it's going to do a lot of the right things. So we really are using it to make sure that we are living on the support we want to live on. Right. So if you want to live on 0, 1, then you might use a logit transformation. Here we're using a log link. If you want to stick with Poisson. So we want to stick with Poisson, the positive real numbers. So in principle, those rates, if you collect enough data, the rates would never go down below 0. But why? Why would you even entertain that? Okay, so a few comments. In the usual Gaussian process setup, we write the field observations as the computer models of simulation. Here, the computer model informs the latent mean. So I've already said that. the latent part of the model. And so we're going to have to feed itself through the link function and the likelihood in order to do the full analysis. And there's many types of data for which this happens. You can deal with sensor data and things like that. So for a lot of you would say, well, where would you get sensor data in a computational model? Some of the shock tube experiments that I've dealt with at the national labs, the simulator will say that the shock has left the tube, so to speak. The shock is, and so it's a sensor type of observation, right? Okay, I'm going to skip some of this. So our inference is easy enough to put together a likelihood. What you have is a Poisson likelihood. You've got this function for the rate, and you've got model parameters. So you can just put this together as likelihood and prior sort of thing, and not that big a deal. So it's kind of what you would expect if you're putting this all together. Why is this here? Well, it makes it look like I'm doing math, but I'm not really. Okay, now you do have to be a bit careful on how you do these things. So if anybody, this is more of a disclaimer for anybody who ever watches this talk, the one lonely person. Hello. Anyway, as you set up your priors, you want to be thoughtful about some of the bits and pieces, right? So length scales have to do with how smooth you think the function is, right? You should be asking that question before you run an experiment. Now when it comes to these variance components, or in our case precision, so 1 over the variance, think of it like that in your Gaussian processes, one of the things that can happen with real data is that they start trading off with one another. So in the Kennedy-O'Hagan model, if you're not careful, what you'll end up doing, you have this discrepancy plus noise portion. And if you're not careful, then what will end up happening is the discrepancy will just interpolate the noise, and the noise variance will go right down to 0. So these are simple things, and but they're things you ought to check for. Way we set up our priors is kind of an R² sort of argument or proportion of variability. So we expect, for instance, beforehand, maybe 80 or 90% of the overall variability will be explained by the model. And maybe 10% of the variability will be explained by any discrepancy that you have. So if you start doing this sort of thing, you want to make sure that you think hard about this, because otherwise, because you're operating through this latent mean, it can do a lot of funky things if you haven't thought hard about what the priors would be. Okay, so sampling from the posterior in this case. So single site metropolis can be done. It can take a long, long time. We can use a type of stage random walk that others have used in similar setups for latent variable sort of modeling. I'm going to say as an aside, one of the things that I found to work really well in these cases, without going into the details, is elliptical slice sampling. It's almost magical, and it seems to work really well in this case, whereas single site metropolis will do fine for you, but it will take a while. So you hit enter and take the weekend sort of thing for these sorts of models. So, all right, back to the application. All right, so the goal of the study is to characterize the distribution of impurities, test hypotheses, so on. Okay, we want to test the hypothesis, or at least evaluate whether there's evidence of a discrepancy. So in this case, I'm not going to do a formal hypothesis test. We have done one. We can do one, but I'm going to show you something slightly different. We choose our simulation trials to explore the input space. So we've done the space filling sort of thing, mostly because the sequential design approach isn't going. It's infeasible, given the way that the supercomputers work. All right, so there's our summary. So this is what the apparatus looks like. So this is just a giant graphite brick. It's not that exciting, but it's important to note what the room looks like. So actually what happened was that there was shielding around this. So there was these big white plastic sheets that went around that. And we've got our experiments, our computer experiment runs, which in principle are modeling this apparatus in that room, the graphite bricks, and there you go. We also ran experiments without graphite. So actually what I'm going to do, so I've got two types of observation. I've got, I'm going to call it a baseline observation, which is just neutrons with nothing else in the room. The detector, we've got what do you call it, the source and the detector, and that's it. And in the next one, then when we did the other experiments, we put our graphite bricks. These are individual graphite bricks. And each brick was put through this experiment on the same apparatus. All right, so what do I have? I've got my calibration experiment, which is the 6 graphite bricks, and I've got my simulations, which are my 64 trials. What I also have is 64 trials of graphite through air. And I've only got one trial of graphite through air, and I've got observations of no graphite observations. Right? So that's what I'm trying to say. All right. Now each brick, so this is really just here to tell you that there's an exposure time that each brick is undergoing. And what we're actually going to model at this case, so what's funny is that the quantity of interest can change on these things. But what we decided to do, the most stable observation we could actually have was the ratio of the counts that we observed with the graphite there to the ratio to the counts under when there was just air. So there was no graphite in the room whatsoever. So what we end up modeling in that case is the attenuation, right? So think of it as the proportion of neutrons that are accounted for by the graphite or absorbed by the graphite. Okay, so that we're going to call it alpha theta. So the model looks kind of like this. We've got observations in air, and which we view as a Poisson distribution with a particular rate, and then you also multiply that by the exposure time. And our model, our observations with graphite will be an attenuation model, if you will, with a particular theta, and that theta is an average impurity associated with that individual brick. Okay, and we want to characterize the distribution actually of those thetas. And that's times the actual rate and the exposure time that the graphite undergoes. The prior distribution on the thetas will be Gaussian, okay? And we use a logit transformation. And the reason for that is the attenuation has to be between 0 and 1, right? You're not going to get more neutrons because you put graphite. And that happened with an initial code run that we had, by the way. One of the things you can evaluate your models is when you get something crazy, like more neutrons when there's no absorber. Oh, sorry, when there is an absorber, right? So something supposed to suck in neutrons gives you more than you're supposed to have. All right, let me just show you a couple of plots. What I have here are the model runs, the computer model runs are the black dots. And we just put them on along each of the individual inputs, right? So over on the far right is the impurity concentration, which varies between 0 and 1. And what you see are the model runs, and why are they not all landing on top of some curve? Well, the axial position and source radius have changed. So those are the all 64 runs. The curves going across, the bars going across the lines, those are the actual observations. Okay, those are the observed ratio between the neutron counts of each brick divided by a baseline in air. All right, so what is this saying? Whatever we do, whatever statistical procedure you're going to have, it should agree with a fairly low, relatively low impurity concentration, a relatively high axial position, and it doesn't look like we're going to learn a whole lot about the active source radius. Okay, so whatever you do in your inverse problem, this is probably what you ought to see. So we're going to do the calibration right now, and what we end up with is a posterior distribution. So I'm going to turn that crank on that model, and I'm going to end up with a posterior distribution of the average impurity for each of the 6 bricks, and that's what I'm showing you here. Okay, they all look pretty similar. Now it turns out that they didn't know. They just had, so this is a nuclear engineering department. They had a bunch of graphite lying around from other experiments, and it turns out that they didn't know this, but this is actually reactor grade graphite, and they discovered this. This is what you would expect the impurities to look like. Now, but when you wrap that up, what you actually want is this. Is a distribution of impurity concentration. So we have a family of possible impurities, because if we're going to make predictions on future bricks, we don't know those impurities. Okay, so we want to be able to make a prediction of that. What this is also have the posteriors for the source radius and the source position. And as I said, you have relatively large source position, and we're not going to learn a whole lot about the source radius. All right. So then what do we do next? We run the code again, but for a slightly different apparatus. And that apparatus is 2 bricks instead of 1. Okay? Same level of complexity in terms of the calculation. And then we're going to make predictions. All right, so these are the simulation runs, the black dots. Those are the simulation runs for the new apparatus. Now we can make predictions. There's the model. But we also can use the impurity to help us. Right? So if it was just model, we would say it's somewhere between 0 and 0.05. But we know something about the impurities, or the family of distribution of impurities, so what we can do is sample from that posterior, and we can propagate those across an emulator using those 64 runs, or however many runs there are of the new ones, and that would give us predictions. and or give us predictions, if you will, or distribution of predictions, and I can make a prediction interval here, if you like. If what you're going to do is assess your model's capability by looking at prediction intervals, and then what I can do is collect new data and evaluate the model's ability to predict, right? Say, you know, if I did a bunch of new experiments, maybe I would expect them to land in there with probability 0.95, right, if the model were correct. Right, so this is a real success. We collected some data. There you go. That's not good. Right, so, okay, so I don't know if anybody was expecting a success here. So this was not a success in terms of what was going on. So when this happened, right, so they were like, oh, this is an easy one. This should be no problem. Now, if you notice, you can forget about statistics here. None of those black dots are where the data are, right? So what this is telling you is you're getting more neutrons. So this is a process of code development and statistical feedback and assessment and et cetera. So right now, as a statistician, first when I saw this, I thought, oh, this is not good. And then I thought, oh, well, this is a success for me because my prediction intervals, you know, give what they give, and I'm telling them their model. I'm feeding back to them and saying, listen, we need some more development on the model. Okay, so I get to, at least I'm not to blame. So that's okay. So what do? So it turns out that the model was not taking into account the backscatter from this crate here, as an example. There's something like that. There's a crate there, and in fact, there's a certain amount of even in the next level of experiments, there's a certain amount of boron that's actually in that polyethylene. Those polyethylene sheets. And so, so what is the moral here? They're actually, part of the moral of the story, do you know her? Okay, no. No, I'm going to blame her at the end, by the way. I don't know who that is. She's just in the picture, but I'm going to blame everything on her. No, hopefully she doesn't see this. Anyway, okay, so one of the things that actually happens I mean, the truth was, the model wasn't modeling the experiment. Right? It wasn't taking into account the backscatter that you're going to have, or the room shine, or it wasn't properly accounting for the materials of the walls. And so what happened? We ended up getting more neutrons observed. You know what's happening is the neutrons are going up, getting reflected back down into the counter, into the detector, and that's what you're getting. You're getting room shine. And if you don't properly account for that, then it turns out the model may be doing the right thing, but it's not modeling the experiment. The experiment's actually a different thing. And that's where, in our case, this discrepancy comes in. Yeah.
So to continue on, did you actually simulate the detector itself, not just count the number of neutrons that made it through in your radiation transport simulation? So what I'm saying is that you would create a geometry that resembles that of your detector with whatever material your detector is made of, presumably sodium iodide, in this case, and then count the number of...
So all that was done.
Okay.
Yeah. Okay, so we did new calibration experiments, and I'm going to tell you, I'm not going to show you the results, but we moved on, and in fact we were able to calibrate, and the predictions were actually within our prediction intervals. We do other things for assessment. Let me just say that if that's what prediction intervals aren't the only thing you'd want to do. You want to look at the distribution of the counts. You want to look at the distribution of of what you've seen of the observations in the experiment. You have a lot of things you can compare, and we do those things. All right, the other thing that you should know, that as part of this code development, there's other things that are happening continuously. So the model is changing and has been improved as we've gone along, and we've tried to calibrate under different scenarios for what was actually happening in, like, for instance, we're using a rectangular mesh geometry, et cetera. So what's the point here? The point is that part of this is also the assessment of the model under different implementations, and that's actually happening as part of this project as well.
You said there was no discrepancy involved. So how can you improve that?
So the answer is the discrepancy is clearly in the calculation, right? So there's two types of discrepancy that you're going to see. It's your ability to calculate what you want, and in this case it was, are you actually modeling the thing that you think you're modeling? So what we found now, I mean, I should have brought this up, is that, we did similar type of thing. So similar type of experiment, or same experiments actually. And can you validate, if you will, and then you proceed onwards, and we were able to proceed on. Now, what is that discrepancy going to be? The discrepancy will be based on its numerics, right? I mean, it's not. It has to do with implementation, and the ability to calculate what you want to calculate. And there are bounds for that people people put a lot of work into getting. And the question is, are you within that? So what I would put in here, let me just tell you that some of the stuff that we have done. I'm going to go back, and go back here. All right. So what would our discrepancy be for, in this particular case? What we actually do, oh, geez, I'm going to keep going back and forth until you ignore me, until you give up on the question. So where we have our attenuation, the exposure, what we actually put in test for is alpha f plus discrepancy times, put a bracket around all that, times the rate and the exposure. So with the idea that the discrepancy was going to get worse it's going to accumulate as the exposure time goes up. So that's what we'd be testing for. Am I running out of time? I think I have 15, right? Okay. All right. Okay, so let's go back to where I was. So, right. So this is where I was. Okay, so we've managed to move on, but we have not moved on to the full 5-year experiments because we continually are adjusting that implementation. So the other thing I'm going to say is, go back here. So as practice, right? So you move down this hierarchy. So this is we do this second experiment, and we make predictions on the next experiment. If we can't validate, then the code has to be addressed, if you will. So we try to discover what the what's possible about the implementation that is not giving us the ability to predict the experiments. You have to go back to the beginning. So we can't run new experiments because we'll just take way too much time. But you can't calibrate going forwards without calibrating backwards. So you have to go back to the beginning and say, okay, does the code work on the simple experiments too, right? So then you got to go down this pathway and make sure you validate on all the levels of the hierarchy with the new version of the code. Okay? Because otherwise you're just calibrating or you're adjusting to level, but you're you're predictive on a level, but maybe not other levels of complexity. Okay, so in our context, the impurity model, okay, when we say validate, there's other things. So it's nice to say we know the model, we know the physics, there's bits and pieces in the background that's nice to say. So what is actually being validated? Well, the equations, the parameters, so cross sections. You're conditioning on the cross sections, the geometry, composition, boundary conditions, discretization, et cetera, et cetera. So the statistical model is way at the bottom, I think, of this list. But it's we'll assume the statistical model is fantastic and does everything you want. But there are other things. When I say that we're validating the model, it's not as simple as saying. There are real details to the implementation that matter. And those are the sorts of things that we also look into, thinking hard about. We have switched the cross sections as an example. The Los Alamos cross sections weren't very helpful for this particular one, and we thought that they would be. So there you go. So I think I'll wrap up there, and I think that we have a framework in which we're able to use model calibration as a way for generalized linear models. I'm going to say, at least in this hierarchical validation framework, which I think is useful. In this case, we're interested in the calibration distributions, which is a small twist on what you typically see, where people are interested in a parameter, but it's not unique to this problem. And I think one of the things that is new here is in fact the framework in trying to feedback code development and experiments and within this computer experiments world. So I think I will stop there. Thank you.
So in
Better be easy, Matt. I can take that PhD back.
Conceptually nice and easy. It's something I think you'll have good feedback on. But so like in traditional experiments, kind of a standard blocking effect you might want to consider is operator if you're looking at, like optimizing some factory process, right? Mm-hmm. And then when we do computer experiments, we always say, oh, it's we're doing the deterministic ones. We say it's deterministic and we don't have to worry about any of this type of stuff. But I think in complex models, that's not actually true. I think that if you take scientist A, who's an expert on nuclear physics and runs the models for you, the way they might tune it and spin it up to get the output might be different than what scientist B does.
So okay, so we can only take care of so much. I think there's a couple of things. So there really can be an operator effect. So for those people who don't think about this, so this is one of the statistical problems that comes up as an undergrad, is if you're collecting data and say you collect the data for some experiment in a lab, and the person next to you also does the exact same type of experiments in the same lab, you don't get the same results consistently. There's some little bit of operator effect that there's an individual effect to actually collecting the data. So what Matt's saying is, well, actually, I can tell you that happens on the physical data side. Here, it really happens, and it could happen on the computational side. So I don't know how to take that into account because we have Daryl Hawkins who does all of it. So Daryl is the guy who's really working hard to make this stuff ramps up in the right way and that sort of stuff, at least on the supercomputer. So we have one implementation, and we could add a potential random effect to that, but I wouldn't even know what to do with it. But conceptually, it's there. It could be there, yeah. Other questions? Yeah.
I didn't quite get what you were talking about, something collapsing in the calibration with the model discrepancy term between the observation noise and the...
So I'm not exactly sure where I'm supposed to be for that. I'm going to go back to something.
Yeah, it was when you were talking about kind of forming the discrepancy term, you talked about something, I think actually it was a couple slides after this.
After this.
You also said it grew with time. If I'm
Oh, is that the attenuation? So what I was talking about was probably not here. So what I was saying was this. So it was more of a conceptual thing. Sorry, I'll answer a question that might resemble the one you asked. So what I was saying is that there's usually this framework allows for a systematic discrepancy between model and the mean in the physical system. And often, so that discrepancy is put in there to try to at least take the observations and somehow describe that. Conceptually, in this project, if we can resolve everything we need to resolve and compute everything we need to compute, and the physics really is perfectly known, then, well, maybe we won't be able to compute everything that we want to. But if we could, there would really be no discrepancy. Okay, we'll go with that as our starting point. But there's going to be an implementation. There are errors. Based on any discretization, there's going to be some level of tolerance that you're clearly willing to accept. If the model is actually the right model, and it really is just within tolerance, then that other discrepancy that we usually have there ought not to be there. Okay, so when we test for discrepancy, what we're doing is we're saying, okay, there's the model, calibration distribution. Here's the model itself, because it wants to compute something, and that's the thing we want. But we know that there's a tolerance limit or an error bound that comes from the computation. So we're going to take that into account. There should be nothing left over in terms of error. Okay, that was the part that I think
Okay.
maybe that was the question.
Yeah, that's
Okay,
what I was asking.
all right. Catherine, do you have a question?
Sorry, no, it was more a comment. I was trying hard to understand what operator error meant in the context of two different people running the same numerical code. It was
So I make a fried egg, Matt makes a fried egg, Matt resembles a fried egg.
No, but I mean, if I give you my code and
Oh, and a code.
open it and
Yeah.
I run it, and
Oh, so I
you have
don't.
things that are tunable, which are what could be called tuning parameters. We would think of things like mesh size parameters, stopping tolerances, time step parameters, all of that. You make a choice about certain things when you run a code as the operator.
Mhm.
But I would call those things numerical errors because, it depends on what it is you're actually tuning or fixing, of course, but a lot of the choices you make as the operator result in discretization errors, numerical errors.
Right. Okay. So I'll also throw in there what's really strange. I don't have a fully. Some maybe other people in this room have a grasp on this, but if you were to take this implementation and drop it on another supercomputer, you'd get different answers
Yeah.
some of the time, even though all those tolerances are supposed to be the same. So I'm not sure. I'm not sure what would be in
About
that
the
case.
human aspect of
Okay.
it.
Yeah. So I'm not entirely sure. I'm just assuming Daryl does a great job. So you should all have a Daryl too. Okay. Any other questions? All right.
Perfect then.
Well, thanks
Thank
for
you
your time.
once again.